Gears provide one of the most common methods of transmitting power. To meet different requirements, gears of different designs are produced by skilled craftsmen in machine shops. The simplest type of gear is the spur gear. Its teeth are parallel to its axis. This type of gear is often cut on the milling machine. The average blueprint of a gear usually contains terms peculiar to gear designing. Therefore, an understanding of these terms is helpful to the machinist. The basic figuring all tooth dimensions on a gear is an imaginary line called the pitch line. It is on this line that the thickness of the tooth is always measured. The distance from the pitch line to the face of the tooth is called the addendum. The distance from the pitch line to the base of the tooth is called the dedendum. To provide sufficient clearance when the teeth are engaged, the dedendum must be greater than the addendum. These are the terms applied to the parts of any single gear tooth. In the gear as a whole, the pitch lines of the teeth form a circle called the pitch circle. The number of teeth per inch of pitch diameter is known as the diametral pitch. This can be simply illustrated. This gear has a pitch diameter of 3 inches, and it contains 12 teeth. For every inch of pitch diameter, there are 4 teeth. Therefore, the diametral pitch of this gear is 4, or as more commonly expressed, this is a 4-pitch gear. This gear has the same pitch diameter, but contains 15 teeth. Since it has 5 teeth for every inch of pitch diameter, this is called a 5-pitch gear. In other words, the diametral pitch is always equal to the number of teeth divided by the pitch diameter, or the number of teeth per inch of pitch diameter. The selection of the proper gear blank stock is determined by the outside diameter, 4 3/4, and the width, 1 3/4. The full depth of tooth is to be 269.5 thousandths, the depth of cut to be made. The number of teeth, 36, and the diametral pitch, 8, determine the selection of the proper cutter. This can be learned by means of a handbook. There are a number of cutters for each pitch, depending on the number of teeth to be cut. In this case, 36 teeth are wanted, so a number 3 cutter is indicated. The cutter selected should always be carefully checked. The specifications of every cutter are stamped into the metal. To cut a gear on the milling machine, a dividing head is used. It consists of 2 parts: the headstock and the tailstock. Both are located in the same table slot. It is between these 2 centers that the work is held. The tailstock can be adjusted at various heights and angles. For a straight cut, as in milling a spur gear, the tailstock is set horizontal. This can be done accurately by means of a calibrated scale on the rear of the tailstock. To ensure a rigid cutter setup, the table is moved as close as possible to the head of the machine. The cutter is lined up with the approximate center of the headstock. After applying the key and the remaining collars and arbor support bushing, the operator rigidly secures the cutter setup. While there is still sufficient clearance around the arbor, the center of the headstock is lined up accurately with the center of the cutter. The centers of cutter teeth are marked for this purpose. The saddle is locked in this position. Next, the table is lowered to provide room for setting up the work. To hold the gear blank in place, a mandrel with an expanding sleeve is used. The mandrel is tapered. The operator centers the expanding sleeve in the gear blank, inserts the mandrel, and drives it solidly into place with a soft hammer, which should be either of lead or rawhide. Before placing the mandrel between the centers of the dividing head, the tailstock center is lined up squarely with the headstock center. Sufficient room is left between them to hold the mandrel before the tailstock is secured to the table. Then the centers are checked again with a surface gauge. Next, the operator secures a dog to the mandrel. The mandrel is held against the headstock by the tailstock. The dog is held solidly in position by a set screw. Notice that the large end of the tapered mandrel is next to the headstock, so that the thrust of the cutter will tend to tighten the gear blank on the mandrel. The operator centers the work directly under the cutter. The table is raised by hand until the cutter just scrapes the gear blank. It is from this position that the full depth of the cut is calculated. The index dial of the vertical feed screw is set at 0. Then the work is moved away from the cutter. The second function of the dividing head is to accurately locate the desired number of cuts on the gear blank. Each full turn of the crank rotates the gear blank 1/40th of a turn. In other words, there is a 40-to-1 ratio between the movement of the crank and the movement of the work. Suppose we had to cut 4 equally spaced slots in a disc. 10 turns of the hand crank will turn the work 1/4 of a turn, locating the second slot accurately. Ten more turns will turn the work another 1/4 of the way around, locating the third slot. And 10 more turns will turn the work the last 1/4 of the way around, locating the fourth slot. The operating principles of the dividing head can be further simplified by imagining the hand crank to be centered directly in front of the work. If 40 equally spaced cuts were wanted, each full turn of the crank would move the work 1/40th of a complete revolution, thus locating each of the 40 cuts. If 20 cuts were wanted, 2 full turns of the crank would move the work 2/40ths or 1/20th of a complete revolution, locating each of the 20 cuts. If 10 cuts were wanted, 4 full turns of the crank would move the work 4/40ths or 1/10th of a complete revolution, locating each of the 10 cuts. 8, 5, 4, or 2 cuts could be located just as easily, because they too can be divided equally into 40. In other words, dividing 40 by the number of cuts required will give the number of turns of the crank necessary to locate each cut. This establishes the formula 40 divided by n, the number of cuts to be made, equals T, the required number of turns of the crank. Up till now, we have only considered making cuts in numbers that go into 40 evenly. But this job calls for 36 teeth, which means making 36 cuts. From the formula, 40 over n equals T, 40 divided by 36 equals 1 1/9 turns. After making the 1 full turn, the problem is to make the additional 1/9 of a turn and make it exactly. To do this, it is necessary to divide the plate in back of the handle into 9 equal parts. Turning the handle the distance of one of these divisions provides the additional 1/9 of a turn. Standard indexing plates are provided, which make it possible to accurately locate whatever part of a full turn of the handle may be required. Each number on the plate indicates a circle consisting of that number of holes. The crank can be adjusted so that the locating pin will enter the holes of any desired circle. Because there is no 9-hole circle on the plate, the operator selects the smallest number that can be divided evenly by 9. In this case, 54. Since 9 goes into 54 6 times, moving the pin 6 spaces on this circle turns the handle the required 1/9 of a turn. To simplify the operation, a sector is used as a gauge. Adjusting the sector to 6 spaces eliminates the necessity of counting out the number of spaces each time a cut is to be located, since the distance between both blades of the sector equals 1/9 of a turn. Moving the sector against the back of the pin automatically locates the starting point for the next 1 1/9 of a turn. As the pin approaches the proper hole, the handle should always be moved slowly. If it is moved past the hole, always move the handle back at least half a turn and then bring it up to position again slowly. This will take up any play that may be present in the gears of the dividing head and prevent over-indexing. Before the first cut is taken, the indexing calculations must be carefully checked. For this purpose, Small nicks, about 1/4 inch deep, are made around the entire gear blank. After the last nick has been made, the operator counts the number of nicks and checks with the number of teeth called for in the blueprint. "36. The head is indexed for another tooth. Then the cutter is brought up to the first nick by hand to be sure it trues up in this nick. This entire procedure, making trial nicks, counting them, and checking the location of the cutter in a nick, is one of the most important steps in cutting a gear. With the dividing head correctly adjusted for locating each cut, the depth of cut is next calculated. The full depth of tooth is to be 269.5 thousandths. Since the gear must be finely finished, 2 cuts are required. The second one a finishing cut of 1/16. Therefore, the first cut will be the full depth minus 1/16, or 207 thousandths. Each division on the vertical index dial represents 1/1000th of an inch. So the operator raises the table 207 divisions for the roughing cut. A conservative cutting speed for the cold rolled steel gear blank will be used, 90 feet per minute at the teeth of the cutter. Since the cutter is 3 inches in diameter, its circumference is almost 8/10 of a foot. Therefore, the cutter speed should be 115 RPM. The nearest speed to that calculated is selected, 116 RPM. For the first cut, a chip thickness of 2 thousandths can be used. The cutter has 12 teeth, and in one revolution will remove 24 thousandths of metal. With the cutter turning at 116 RPM, it will remove 2 784 thousandths of metal per minute. The operator selects the nearest figure on the feed dial, 2 3/4 inches. The work is further supported by a table jack. The first roughing cut is then made across the gear blank. Notice that a flow of coolant has been provided to lubricate the teeth of the cutter and to keep them cool. When the first roughing cut is completed, the operator stops the cutter. With the table in this position, an automatic table stop is located to prevent the indexing head from running into the cutter on the subsequent cuts. Another stop is also located to save time when the work is moved back to the starting position for each new cut. Now, the operator is ready to make the balance of the roughing cuts around the gear blank. For the 1/16 inch finishing cut, the table is raised an additional 62 1/2 divisions from the starting point of 7, giving a final reading on the vertical index dial of 69 1/2. Since the depth of cut is small, the speed is increased, and the rate of feed is decreased to ensure a fine finish. Next, 2 trial finishing cuts are made, just deep enough to check the thickness of one tooth. The thickness of the tooth is always measured on the pitch line. The reading must correspond to the specifications called for on the blueprint. The finishing cuts can then be made around the entire gear. It should be noted that the actual cutting of work on the milling machine is the smallest part of any job. For if the proper cutter is selected, a cutter stamped with the specifications called for on the blueprint, if both the work and the cutter assembly are rigidly set up, if the location of each cut has been accurately calculated with the dividing head, if the proper speed and feed have been set, and if the entire setup has been carefully checked before making a single cut, then the last step, actually producing the work called for, is a relatively simple procedure. And the result is a spur gear cut exactly to specifications. A gear that will pass every test made to check it before it is put to work to perform its important function of transmitting power from one moving part to another.